Welcome to The Explainer. Today, we're taking a deep dive into a topic that's absolutely fundamental for modern .NET developers, but honestly, it's incredibly easy to get wrong. We're talking about async and await in ASP.NET Core. I am super excited to guide you through this, because mastering these concepts, it's literally the key to building highly scalable, responsive, and bulletproof web applications. We're going to take those complex internal mechanics and break them down into crystal clear, actionable concepts. So let's jump right in. Seriously, are you secretly starving your server's thread pool? It's a very real question. You know the drill. You write some clean-looking code, it compiles perfectly, it passes all your local tests with flying colors. But the absolute second your application gets hit with heavy user traffic, bam, it grinds to a halt or just crashes completely. Well, why does that happen? A lot of the time, the hidden culprit is bad asynchronous code. Today, we're going to uncover exactly how that happens and, more importantly, how you can prevent it. Here's our roadmap for the day. First, the waiter analogy. Second, inside the state machine. Third, the ASP.NET Core thread pool. Fourth, parallel e-commerce tasks. And finally, we'll wrap up with 3 golden rules. Section 1, the restaurant waiter analogy. To really grasp what's happening under the hood, we need a rock-solid, real-world mental model. Before we hit the restaurant floor, let's just make sure we're on the same page with our core definition. Asynchronous execution simply means performing tasks without blocking the main thread. So while a task is happening, like say a database query or an external API call, the thread doesn't just sit there frozen in time. It's freed up to go service other operations. C# Corner uses this brilliant scenario that perfectly illustrates the concept. I want you to imagine a waiter in a busy restaurant. That waiter? That's your server's thread. The waiter goes to table 1 and takes their order. That's step 1, starting the task. Then, the waiter hands that order to the kitchen. Now we hit step 2. The kitchen actually has to take time to cook the food. That right there is our I/O pause, just like waiting for a database to return data. Now, a bad waiter, a synchronous thread, would literally just stand completely still, staring blankly at the kitchen doors until the food is ready, totally ignoring everyone else in the restaurant. But a good asynchronous waiter? Step 3, they immediately leave the kitchen to go serve another table, take more orders, keep the whole restaurant flowing. When the food is finally ready, the kitchen rings a bell, and the waiter comes right back to finish serving table 1. That is exactly what async and await does for your web server. Okay, section 2, inside the state machine. Now we're zooming in from that high-level analogy right down into the actual C# compiler mechanics. It's kind of wild when you think about the massive contrast between our developer experience and what the compiler actually has to deal with. What we write is so clean, right? Just a method signature with the async keyword and an await before a task. It looks exactly like standard top-to-bottom sequential code. But what the C# compiler builds behind the scenes? Completely different. It literally rips your method apart and reconstructs the whole thing into a highly complex state machine. This quote from C# Corner really hits the nail on the head. The compiler does not just run your code directly, it converts your method into a state machine. We need to completely shatter this myth that adding the async keyword magically spins up new background threads to do the work. It doesn't. The state machine simply orchestrates the pausing and resuming of your code. It's basically saying, hey, start this task, pause execution right here, return control to the caller, and when the task is totally done, resume exactly where we left off. Moving on to section 3. The ASP.NET Core thread pool. Let's look at how that state machine interacts with your server's precious resources. 0. That is a massive, very important number for modern .NET developers. As the well-known expert Stephen Cleary pointed out in a really popular Stack Overflow discussion, modern ASP.NET Core has exactly 0 default synchronization contexts. You see, legacy ASP.NET used to have this context that actually forced asynchronous continuations to hop back onto the exact same request thread. Well, ASP.NET Core threw that out the window. They stripped all of that away for maximum performance. And here's the absolute lifeblood of scaling your app. Releasing threads to the pool during I/O pauses is what prevents server starvation. Because we don't have that synchronization context tying us down anymore. When your async method hits an await for, say, a database call, that thread is instantly released back into the server's thread pool. It can go serve a completely different user's web request. When your database call finally finishes, any available thread from the pool can step in, pick up the state machine, and finish returning the response. This is how you handle millions of concurrent requests without crashing your whole system. Section 4, parallel e-commerce tasks. Let's tie this all together with a practical, heavy-duty e-commerce scenario. There was this really fascinating benchmark discussion on Stack Overflow that tested exactly this kind of load, concurrently downloading 5,000 product photos. If you do this sequentially, meaning you wait for one single photo to finish before starting the very next one, it takes 24 long minutes. But if you use parallel.for each async, that time drops dramatically to 5 minutes and 19 seconds. Better yet, if you use task.oneAll, it completely plummets to an incredible 1 minute and 7 seconds. So you might be wondering, what's up with that 4-minute difference between the two parallel approaches? Well, the answer comes entirely down to concurrency limits. Task.winAll fires off all 5,000 network requests at virtually the exact same time. It's like a fire hose of unlimited concurrency. So yeah, it's incredibly fast for I/O operations, but it's also risky. As the Stack Overflow community pointed out, if you launch 5,000 simultaneous requests, you might just trigger anti-DOS security limits on the remote server and get yourself blocked entirely. Parallel.for each async, on the other hand, is throttled by default based on your server's CPU cores. It automatically balances the work safely. So basically, winAll is faster, for sure, but for each async is much safer for server resources. Picking the right tool here is absolutely crucial for your app stability. Section 5, 3 golden rules. Let's zoom back out from all those deep technical mechanics and look at 3 best practices you can start using today. Software engineer Oleg Kurlchuk shared these, and they are basically the non-negotiable rules for writing stable async code. Rule number 1, async all the way down. Number 2, return task not void. And number 3, avoid .result or .wait. Let's break these down one by one. Rule 1 is async all the way. Listen, if you have an endpoint that calls an async service, that endpoint itself must be async. If you mix synchronous and asynchronous code, like having a synchronous method call an async method, you completely break the chain. The thread just gets blocked waiting for the async operation to finish, which totally defeats the purpose of that beautiful state machine we talked about, and it'll kill your app's performance. Rule 2, return task. You should almost never, ever use async void. If you write an async void method, whoever called it has absolutely no way to await it. And it gets worse. If an exception happens inside an async void method, it just gets totally swallowed. It can literally crash your entire process, and you wouldn't even be able to catch the error in a try-catch block. The only acceptable place for async void is in UI event handlers. Literally everywhere else, always return a task. Rule 3, avoid .result or .wait. Guys, this is probably the most dangerous mistake a developer can make here. If you call an async method and just slap .result onto the end to force it to run synchronously, you are practically guaranteeing a sync over async deadlock in certain environments. You are physically holding the thread hostage. You're refusing to let it go back to the thread pool while the async task is waiting for a thread to complete its work. It is hands down the fastest way to completely lock up your application. Just don't do it. Always, always use await instead. One last thing I want to clear up. A heavily debated topic on Stack Overflow. Configure await false. Do you actually need it? Well, the answer depends entirely on what you're building. Remember how ASP.NET Core apps have 0 synchronization contexts? Because of that, calling configure await false in your app code is completely redundant. However, if you are building a reusable NuGet package or a library that might be consumed by older legacy frameworks or desktop apps that have a UI thread, you absolutely must use configure await false. That's how you prevent deadlocks in those specific environments. So I want to leave you with this provocative thought to chew on. Think about the legacy code, or hey, even the brand new microservices your team just deployed. How many hidden .result or .wait calls are lurking in your codebase right now? Are they just sitting there waiting for a massive traffic spike to completely starve your thread pool? I highly encourage you to go run an audit on your code today. Hunt down those blocking calls and replace them with proper awaits. Because once you let your threads act like those efficient restaurant waiters, you'll finally unlock the true scalability of ASP.NET Core. Thanks so much for joining me on this explainer, and happy coding.